Hello, everybody. It's Compose Multiplatform Performance on iOS talk. My name is Elijah Semyonov. I'm a JetBrainer and iOS engineer in Compose Multiplatform team. So, in case you don't know what Compose Multiplatform is, it's a declarative framework for sharing UIs across multiple platforms based on Kotlin and Jetpack Compose. By the way, is there anybody who still hasn't tried iOS Multiplatform Compose? Officer, these people right there. Okay, so right now we have many supported platforms. It's Android running on top of Jetpack Compose and its own virtual machine. It's desktop, which currently supports Linux, macOS, and Windows, where the Kotlin language is run on top of Java virtual machine. We've got iOS, which is currently in beta, which runs on Kotlin, which is compiled to machine code. It's Kotlin native. And web, which is currently in alpha, where we compile Kotlin to WebAssembly. So one of the main goals for us is providing consistent user experience across all platforms, and that includes a heavy focus on performance. So just in case, consistent user experience implies crashes on all supported platforms for Kotlin Conf application when the schedule moves. So this talk covers definition of what performance is and what our goals are, overview of Compose multiplatform machinery and how it works in iOS, and summary of interesting problems we had and how we overcame them. So what is performance on mobile devices? In our view, it's max and consistent refresh rate, low latency between input and visual feedback, fluid and smooth visual changes, and also avoiding unnecessary work to avoid battery drain and thermal throttling. So let's get started with Compose itself. The core idea in design of Compose is pretty simple. We just have functions with composable annotations which call each other with way we can describe some interface. So here's a primary function called application. It has a column and 3 other functions which eventually have free text inside. So how does all this beauty come to be? We call Compose Multiplatform framework and not a library because it relies on a tandem of Kotlin Compose compiler plugin and Compose libraries. Compiler transforms code. It enters a lot of metadata about the code flow, inserts extra function calls to the runtime, and adds extra arguments to composable functions. So runtime uses this data to figure out when and what to execute to run efficiently. Jetpack Compose is pretty much the same thing. Also, we have this UI library, which contains layout, modifiers, gestures implementation, foundation, which contains fully fledged UI blocks like text fields, and material, which is a material design library, which is built on top of that. So coming to our application, let's figure out why runtime and compiler are so cool. Application, in fact, here is a pure function. It doesn't really have any state and doesn't take any arguments from outside. It will be most probably executed only once and cached for future invocation, and it provides the same result whenever it's called. Usually when we are speaking about results, we imply returning a result, but these functions don't really return anything. In general, it's allowed to return stuff from composable functions, though. This result is actually emitting some data here. We described the interface. We have a column, we have text, so some data is there. But we need a context like to emit this stuff into. So composable functions have that context, and they can only be called from other composable functions. So basically, these composable functions have a color, just like suspend. Suspend functions have dispatching context, and composable has composable machinery inside, which is implicitly passed. So execution of composable functions happen on a stage of machinery which is called compose. In this stage, runtime keeps track of the called composable functions, the arguments they take, the immutable states they use, and detects which function actually needed rerunning and recomposing. And some of these functions are special. I marked them in red on this slide. They contain a special call which is called layout. And what this layout does inside, it emits a compose node. So, in fact, we could say that result of execution of our application function is just emitting a tree of compose nodes into compose machinery. And compose runtime, in fact, is agnostic about node types. But we do UI framework, so the exact type of emitted nodes is layout node. So we have a layout node tree in the end. And it's called like that for a reason. Layout nodes are aware about how they should be laid out. And when they have this tree, we can proceed to the next stage of composable machinery, layouts. In this stage, we traverse the tree of nodes and measure them and place them according to their policies and the policies of their containing nodes. So column knows how to lay out its internal digits vertically, and text know what size they should take according to the constraints which are imposed from the column. So and then the layout is done, we can basically draw something. Next stage is draw stage. We traverse the tree again and ask nodes to draw themselves if they have anything drawing modifiers attached. For example, column by default doesn't really need any special treatment because like there is nothing to draw. But text widgets will draw the text glyphs on the screen. So this logic forms the main sequence of Compose machinery. It's compose, layout, and draw. Now that we have an idea about how it all works, let's figure out how it works on iOS. Like Carl Sagan said, if you wish to make an apple pie from scratch, you must first invent the universe. So our universe begins with, sorry, it's from another conference, but we can actually pick something in there. Here we create a UI view controller with some Swift UI struct inside and return it. Basically, in our real universe, we do the same. We have a Compose UI view controller, which has a block as an argument, and this block is actually composable. So basically, you can describe your entire interface in there, and it will return you UI view controller. UI view controller is the building block of iOS applications, but unlike iOS applications, we don't really have a UI view or Swift UI view for each Compose digit. Entire iOS Compose UI view controller is just a single view we draw into. So draw is in fact traversing the tree, collecting the commands like fill in something with white color, draw text in this position, and that position, and issuing them to Canvas. Canvas is something I still haven't mentioned. What Canvas is just an interface, abstraction from drawing operations. And in fact, it has two implementations. One is called Android Canvas, which is owned and maintained by Google. And the second one is Skika Canvas. Skika is a library. It's a Kotlin wrapper around the Skia library, which is a C++ 2D graphics library. And it's open source and used in a lot of projects like Chromium. So in order to use this Skika Canvas, we somehow need to write platform-specific bindings to it. On iOS, Skika Canvas is basically just a wrapper around the metal texture. Metal is a graphics API. It's basically just a blob of memory representing some rasterized picture. And then the issue commands to GPU. GPU draws something into this blob. But drawing something into a blob of memory doesn't magically make it appear on the screen. An exclusive way to communicate operation system called iOS how to draw their content on the screen is core animation layers. In fact, every UI view has at least one, and very different flavors of layers for doing different stuff. And luckily, we have a special flavor of core animation layer to draw in using metal. Our UI view has metal layer. Metal layer is internally managing a pool of textures to request and draw into. And it's a highly congested entity. It means all of the textures which is managed could be busy with something at the same time. For example, one metal texture could be used as a bleed source for screen to copy the bytes from. The second one could be used right now by GPU to draw some stuff into. And the third one, for example, could be used by CPU to encode some commands. So it's just a logical entity in there, but still. So we can request a texture, draw something in the canvas, wrap in this texture, and then present this texture on the screen. So this is effectively the last stage of our sequence. The question is, when do we need to execute this sequence? Let's have a look at this really simple Compose application. We have a mutable state, show world, which is by default true. We have a horizontal layout called row, which contains a text, which says hello. And if show world is true, it also shows text world. Along with this function, we also launch a launched effect, which basically just toggles show world back and forth from true to false, and then sleeps for 1 millisecond. So basically, the result of executing this function will be a tree, a variant tree from row, which contains 2 texts, and row, which contains 1 text. The thing is, when show world changes, we meet a special event, which is called invalidation. Invalidation means that the state on which UI depends changed, so we need to recompose it and eventually redraw it. But when do we need to do it exactly? Naive answer to do it every time invalidation happens. But the ultimate result of UI framework is something users see on the screen. And we are constrained by how often the screen updates. And this constraint is called screen refresh rate. And there is no point in doing recomputations more often than vertical synchronization happen. So on this slide, you see purple dots. They indicate these invalidation events, with the events where the state on which our UI depends changed. It means we will perform our calculation on this thing which follows any of this invalidation. Unlike other graphics applications like games, we don't need to draw stuff every frame because we want to save the battery and not overheat the device. So Compose layout's draw sequence happens with a precondition. There should be an validation before, after Compose layout draw, if any was at all. And it should happen on following vsync. And also there is a deadline, because we have a timeline of vsync which is independent from us. And if we fail to deliver our drawing results on time, we drop the frame, and the user will experience a visual stutter. So when a lot of stuff is happening, things can go sideways if we don't meet our deadlines. So we need to profile our stuff. Usually when people think about profiling stuff, they think about CPU counters. It's in fact a good tool for optimizing hot paths. But how is workload distributed across the timeline? If deadline is missed, why? We need some temporal data. Luckily, on iOS, we have OS log API to signpost intervals of work. Xcode has awesome instruments to visualize it and match with other hardware stats like vsync events. The integrated signpost API of Apple, so workload distribution on timeline in Xcode instruments, is available for every brave soul who calls this function. So when we use it, we can see the pieces of work on our timeline, and now we can basically reason about what's actually going on in there, and if we are late, then why we are late. So let's get back to our goals. One of the goals, the first one, is low latency between input and visual feedback. So let's have a look on this typical frame. Let's imagine some input happened, you moved a finger, for example, and it changed the state on that UI depends. For example, you scrolled something. So it means next vsync we start our Compose layout draw sequence. So we perform it and issue some work to GPU. So GPU starts work. It runs, draws all this stuff into a texture, and then we need to present it on the screen. The question is, should we present it right here, or should we delay it one frame forward? Raise your hands who thinks we should show it right away. And raise your hands who think we need to postpone it. Actually, less people think that we need to postpone. Interesting. But this solution will actually affect whether the latency between input and visual feedback is 1 frame or 2 frames. So it's kind of obvious that 1 frame latency is a good approach and we should chase it. It's also known as double buffering. It's called that because when we work on a frame, that one is currently shown in the buffer. So we have 2 in play, or shown on the screen. But the problem with this approach is that our general budget for time is CPU plus GPU. So if it's more than a frame interval, then they surely miss a frame. And we occasionally have frames where a lot of work is happening. For example, you have some great recomposition with some really drastic changes of your UI, we will lose a frame in there. So, but if we postpone presentation 1 frame ahead, making a 2 frames delay, we allow GPU and CPU to work in parallel, and heavy work can get amortized between the frames. Here we can see on the 2nd frame, our CPU time is actually even more than a frame, but still, we can present stuff in a uniform cadence on this picture, despite everything is being computational heavy. So this strategy is often as triple buffering, and that's the one we use. To sum up, we use triple buffering. We trade off 1 extra frame latency to ensure larger time budget for our workload. So there is much less chances to miss a deadline and have dropped frames, which is much more irritating than a minor input latency. So let's get a little bit deeper in a rabbit hole. How do we know exactly when next vsync is happening? The answer is simple. It's a CA display link. It's a special timer that calls back on vsync. So let's see how it's used. Basically, we say we have an invalidation event, the purple spot in there. We unpause our display link. Some another invalidation event can come, but it basically changes nothing. So when the sync arrives, we pause the display link and start our Compose layout draw sequence. In case the other invalidations arrive in the meanwhile, we just unpause it again. So the cycle continues, and that's how we draw the stuff continuously. And this machinery worked awesome on old 60 Hz displays. But when we started to work on supporting the promotion 120 Hz displays, you actually have never seen or felt like anything before. Apple said that they will redefine your visual experience. I'm not sure about that, but they certainly redefined our debugging experience. So let's say we have a timeline with some invalidations. Things can happen with max 60 Hz frequency, so each frame is around 60 milliseconds. So expect. I would expect pretty much the same thing on 120 Hz, just twice as often. So I've unpacked my fresh developer device, launched the app in a profiler, and my first reaction was like, what the heck is this piece of timeline? If you have no idea what you see right now, you're in the same boat as I was at the moment. But a little investigation uncovered that the reason behind those interesting visuals is that promotion is a variable refresh rate screen. Variable refresh rate screens have interesting shenanigans. Their frame interval is not uniform, so in case there's nothing to draw, refresh rate drops. It means battery life, but how do we control that? Do you remember our old pal CI display link, which we used passively, kind of just listening to it? Well, it also affects the screen refresh rate. So when display link is paused, refresh rate drops to around 10 Hz, and getting back to max refresh rate has some latency, which is over the minimal frame interval, and it's bad. It's bad. So basically, unpaused display link effects are this. It controls what is display refresh rate, and hitting max refresh rate on a variable refresh rate is not instant. So our current unpaused strategy is not valid anymore because we just can't do it on the maximum cadence because there is a latency. So what could we do about it? Perhaps we could never pause CI display link at all? Well, it's bad. It's not free. Hardware will drain the battery even if we don't draw anything. So we could slightly modify our scheduling logic though. Here's the current one. We have an invalidation, the purple dots. We unpause the display link, it's the yellow box, and then we pause it back on draw on next desync. That's how it is right now. So what we could do is not unpause it immediately, but schedule always 2 frames after each invalidation. And in the beginning of each frame, before actually drawing something, we could check if invalidation indeed happened. So in this case, for example, CI display link never gets paused if invalidation comes eventually, and the frame rate is good. And that's always the case with animations, because invalidations from animations are coming inside our main loop during the compose layout draw. So animations are smooth 120 Hz now, but scrolling doesn't feel right. I started to profile it, and I was looking at this picture like, what do I actually see? Like, technically, things are right. I mean, the cadence is like messed up totally, but we have a draw for each invalidation, but these invalidations are coming in 60 milliseconds between them, and the rendering itself, like, has these awkward patterns of 2 frames with highest refresh rate, and basically doesn't make sense. Let's go back to our compose layout draw. Basically, it's technically right. The precondition is invalidation should be after last compose layout draw. So if our state doesn't change, we do not drawing. State, in our case, when we're scrolling, is changed by touches, and they're pushed in iOS system, not pulled, so we can just say, well, where are the touches right now? And it's pushed with 60 FPS even on high refresh rate devices, like, how come? But sometimes it raises occasionally to 120, like, what's going on in there? You remember our old pal, CI display link? Well, it appears that it also affects UI touch push frequency. So at this point, you can blame display link for basically everything. You failed to deliver a feature during the sprint, it's all CI display link. So the workaround for this was kind of simple. Having the fingers on the screen is a good marker that something is about to change, and we need to track the fingers, this high frequency. So just impose it. So when something changes, we do our stuff. And when we raise our fingers, our older mechanism, which was nice at play during the animation fix, everything is perfect, basically. Even if your touches didn't really cause any invalidation, for example, you try to horizontally scroll your vertical scroll, we still keep the CI display link running to ensure that the next actual change is rendered as soon as possible, so there are no stutters and it's really smooth and fluid. So schedule fixes summarize this. We unpause display link for at least 2 frames, we only draw if any validation happens, and we keep it always unpaused while the screen is touched to enforce the UI touch push rate. So But not all performance problems were due to scheduling. Here you can see the picture from profiling the visual effects sample app. It's in Compose Multiplatform repository. And the CPU time here is consistently large, and we are missing the deadlines again and again, and basically a lot of frames are missed, and it feels like shit. So, but why does it take so much time? I started to put a trace on every single piece of code in the main loop and found this awkward guy, CA next drawable. Wait, we were simply sleeping on the main thread, blocked by this function. A small refresh. Metal layer manages a pool of drawable, and it's highly congested. So all drawables can be used at this point. So whenever everything is busy, we simply sleep. What followed after this discovery is quite an interesting takeaway about do not repeat yourself principle. So, do not repeat yourself principle. It seems like a really nice advice, and we kept a lot of our code in shared source set. Basically, we started with desktop, and when we started to work on iOS, we basically just started to only add iOS parts in there. So we didn't repeat ourselves, but if you ask me about how render code looks, like we had to support DirectX, OpenGL, Nettle, and software backends. We also support dynamic library loading, but only on desktop. And there is also rendering IP fallback, so we can try to render something. If it fails, we can try something else and fall back to software in the end. But it only works on desktop, though. So Metal backend in both macOS and iOS, we can reuse stuff. But yeah, no, scheduling is actually a bit different because with core video display link on macOS, and there is core animation display link on iOS. Also, AWT dispatch thread does its own thing, and we also need to control that. So, yeah, by the way, when this move between monitors with different refresh rate, they also should be processed, right? So, we don't do it in iOS, but still it's in there. And there is also custom validation logic, because variable refresh rate, we need some hacks for iOS. And also we have off-screen rendering for desktop. We can write IDEA plugins on Compose, wow. So if someone would ask, can you please describe the call tree and state graph for Compose multi-platform rendering? I would say, oh, sit down, I've got a story to tell. So what we did, we actually just copied all iOS-related code to iOS source set and just collapsed all redundant abstractions, which are not needed for iOS. And it revealed the simplicity behind. We acquired a drawable, and that's basically where we were blocked. And then we created a canvas from drawable. And then we composed, layout, and drew into the canvas made on top of this drawable. But there are actually principles to follow apart from do not repeat yourself. One is called as RTFM, like read defined manuscript. What the manuscript said was this: acquire drawable as late as possible, release it as soon as possible. We failed to do so, and it was not immediately apparent because how complicated the rendering code was. So if you look at these sort of operations, you can clearly see that we acquired drawable way too early. We actually don't need it until the draw happens, and basically compose and layout are the stages which take most of the time, so we can just do it much later. So we can simply swap these two blocks, and then our sequence will be like that. We do compose, layout, acquire drawable, create canvas, and then draw into this. It's good. But can we do better? Let's have a look again at this draw operation. As you can remember, the draw is traversing the tree, collecting the commands, and issuing commands to canvas. The commands they issue is not the same as the ones that are collected, because the commands which are collected are like fill with white color, draw text, like draw gradient, draw some picture in there. And GPU actually doesn't operate with commands like that. It operates with pipeline states, buffers, textures, draw calls. So in fact, there is two stages. It's command collecting, where we collect these abstracting commands to draw stuff, and only then we actually encode these commands, basically translating these abstract commands into something GPU can understand. So our expanded rendering sequence could be explained like that. We compose, layout, then we acquire drawable and create a canvas from a drawable. So we collect and encode commands into canvas, but we can collect commands before acquiring the drawable, or postponing it even further. Let's do it and move the drawable acquisition after the command collection. But how does it actually work on API level? Luckily, Skia has a nice thing. It's called picture, which is basically a command list. So our sequence started to look like this. We composed, layout, created this picture, and created canvas from the picture. And they drew into this canvas. But in fact, like, it's not real, nothing happened. We just basically collected commands in the list. So we acquired a drawable after that, and then encoded this picture into drawable. Actually, there's something interesting about this approach, because we just got this immutable thingy called picture. Maybe we could just move the encoding entirely into a separate thread. Oh, here we go. So basically, on the main thread, we prepare the command lists and just push them to be encoded by the rendering thread. On high refresh rate displays, it was saving up to 30% frame time. It's like, yo, stellar. So basically, look at what we had before. This is a horrible manifest of performance engineering failures. Frames drop, long grain lines, disgusting. Sorry. After all our fixes were applied, it turns into this beautiful picture. It's a dance of workloads, carefully distributed across the cores and GPU. Let's have a long look at it. It's a magnificent view. Oh, yeah, multi-threading. So the problem is that our users couldn't really reproduce it, neither did we, but they saw occasional reports on their crash analytics, so we decided to play it safe for now. We rolled back the separate thread rendering encoding temporarily to the stable last solution. And in fact, it alone was good enough, because we raised our FPS on the sample from 50 to 120, to the max one, and even got some budget left to do even more intense computing on CPU. So, to sum up, we copied the rendering code from common to iOS source set. We collapsed all the logic into simple methods. That revealed that true data flow for us, and this true data flow was unoptimal due to drawable being acquired too early. We started to acquire it as late as possible and almost moved the entire rendering to a separate thread. So no more blocks awaiting next drawable. But what about GPU? We are speaking a lot about CPU, scheduling, CPU. Basically nothing. Skia does a pretty good job, and Compose is not really graphically heavy for GPU, especially for iOS devices, because iOS devices got pretty hefty GPUs. But we have some other place where we could make the life of the device a little bit easier. Native interop. Let's speak about it. Our dear product managers approached our users and started asking them whether they need Compose interop with native UI. Perhaps integrate Compose into UIKit or Swift UI, maybe integrate Swift UI or UIKit into Compose. What about integrate UIKit into Compose, which is integrated into UIKit? User said yes. So we did it. We've got like really cool native interop. We integrate Compose into Swift UI and the UIKit. We can integrate Swift UI and UIKit into Compose. We can basically write UIKit in Kotlin because it's Objective-C, or Kotlin can consume Objective-C to integrate it into the Compose. And basically somebody said that he wanted to integrate Compose into UIKit app, but in the same time he had to use map view as interop view, and he asked to do map annotation view and Compose on top of this interop view. So basically he said, like, can we please have a Compose UI view? No, well, maybe. So let's say you want a native interop view in your Compose app. Basically, we have some canvas and there's some interop view on top of it, as you can see it. But what we do is we cut a hole using the transparent pixel in our Compose canvas. So interop view actually shines from behind. Why? You ask, why don't we actually put it on top? Like, it makes more sense. Actually, there's a trick in that. This approach allows us to use clipping modifiers, shadows on top of native UI without actually re-implementing it natively and using dummy views for shadows, all these things that nobody wants to maintain. And it's a really elegant and easy approach, right? Yeah. With a lot of edge cases, with transparency, blues, the order issues, somebody changes about the traversing order inside the Compose core, so these bugs resurface. So every time somebody makes an issue like that, our entire team like, oh no. Oh, we like those bugs, we fix them. So cutting holes means our layer should be transparent, because operating system can know that in this case, that pixel behind our layer can be potentially visible. And operating system can't really know which one in advance because we didn't render anything yet. So core animation, basically the compositor service of iOS, it really has advanced capabilities for combining layers and coloring. But there is an issue with transform layers. It makes a lot of optimizations, such as direct-to-screen, impossible, so there should be some extra off-screen buffer, and CR returns thread layer longer. Basically, it's not the best approach in general case. So the solution is pretty simple. We just make it opaque when there are no interrupt views. So to sum up, we need transparent meta layers sometimes because interop works like it works right now. But this approach has some overhead. So we just don't do things transparent where there's no interop. Like, why? Oh, but OK, here we go. Let's say we have our 120 FPS, but still I've had some really awkward feeling like something is not quite right. First of all, let's talk about this feeling and about smoothness and about our perception of it. Why do we need high frequency rates at all? The reason for that is simple. Human eye has evolved to be quite good in noticing visual irregularities and inconsistencies, both in static and dynamic. For example, these spectacular uniformly distributed lines are a joy for the eyes, and you can all see it. But if I move them a little bit around, you can see that you can see it. So they're really filthy ones. We should know better. So speaking of dynamics, we've got a lot of animations. When you scroll something, for example, and remove your finger, it starts to decelerate, and the scroll values are actually values interpolated inside our animation machinery. And animations relies on a monotonic clock, which we move forward in order to interpolate values. So what we did is we moved the clock using the Clock System Now API. The problem with that is that nobody really guarantees that now happens in the same cadence between different frames, because quite a lot of stuff can happen on the main thread and postpone all those sync callback. For example, on the main thread, we can use run blocking for network requests, large image decompressions, I/O operations, the usual stuff we do on main thread for the best user experience. So visual change over time was not uniform, and it was possible to notice despite having the max possible refresh rate. But intervals between the syncs kinda are uniform, except this guy, but he got what he deserved. So it's handled, it's all fine. So let's use these three syncs instead. Luckily, we have CI display link target timestamp, so we know from display link when it thinks it will produce. So basically, we can just move our animations forward in time where we assume animations will appear on the screen. And that's it. Our long road towards max frames per second was not in vain. So let's wrap up the things which we did here. We selected a proper latency strategy. We fixed scheduling to properly support promotion displays. We also did do not repeat yourself principle a bit. We optimized row acquisition to avoid stalls. And also, almost implemented a separate thread render command for friends decoding. And we are now using optimal configuration for iOS layer system to make it work easier when it's possible to. Also, we ensure that data-defined and visual change is updated with respect to the actual timeline, so the changes are fluid and smooth. And there's still a lot of work ahead. It was just basically a first sweep. We just gathered some low-hanging fruits. There's a lot of core optimizations, which is done by Google. They basically just rewrite things constantly. We really like these 300 lines PRs. We've got a lot of Kotlin native improvements incoming, such as concurrent garbage collection, a lot of runtime improvements, allocations, etc. So we are going to set up benchmarking and benchmark everything on different devices. And we will also do more attempts on multi-threading, and we will certainly start with proper rendering encoding on a separate thread. Thank you.